All right, everybody, welcome to Duo Tech Talks. How many people came over from Summit today? Yeah, pretty good. Favorite talk? Yeah, there we go. All right, thanks everyone for coming. This is Duo Tech Talks. We do this about monthly. Most of the time here in Ann Arbor, sometimes in Austin, sometimes in San Francisco. We did our first Duo Tech Talk in London a couple weeks ago on hacking video games. I think we have a recording of that coming, so if you missed that, if you weren't awake at whatever time that is Eastern time, then it's going to be up there soon. So we host this event and often bring in speakers on technical or security topics. At Duo here, we're a security company, so we tend to lean towards security-oriented presentations. If you guys ever have recommendations on speakers, we're happy to hear it. Got a few interesting talks coming up for the rest of the year here in Ann Arbor. So one in November, Kelly Shortridge from New York presenting on how to get into security. And I think our December talk is, the speaker's name is Tony from Threat Connect or Threat Metrics, talking about the DNC breach. So that should be interesting as well, given the timing. Any quick local announcements about other security meetups, other events that are going on? ARPSec. Zach, when is ARPSec happening?
First Wednesday of every month, typically. So the next one will be right after
The end of the month.
So we'll have a lot to talk about.
Yes.
That's at 327 Ron Court, typically, which is just down the street from here. So 6 p.m., usually the first Wednesday of every month. You can go to arpsec.org or twitter.com/arpsec to typically find out what's going on there.
Cool. Any other announcements?
There's Ann Arbor Crypto Party monthly. The next one is the second Saturday of November, whatever day that is. You can go to a2crypto.party, and that's a URL. So more info there.
.party, new TLD. Is that Andrew WK's TLD? You could pass for him. So our speaker we have tonight is Erinn Atwater. Erinn comes from the University of Waterloo in her last year of the program. Fingers crossed. We were chatting before about how in a PhD program you're supposed to go like really deep in one topic, but that's no fun. So trying to do a lot of different security research and then forming a thesis out of it, I think, is the real test of a PhD candidate. What Erinn's here to talk about tonight is a very interesting primitive in cryptography. And something that we had dabbled with at Duo early on has been some really strong shelfware over the past few years. But Erinn's going to talk about threshold cryptography and how she's built an interesting application on top of it. So please give Erinn a warm welcome.
Can you hear me? Is this on? Cool. Okay, thanks for having me. So usually I get to start my presentations out with a cute joke about how I'm from Canada and there's 10 feet of snow there. And so I'm really happy to be here where it's warm. But you guys are like an hour or two from the border, so you'll know I'm lying. So I can't do that. So what I'm saying is if none of my jokes are funny, it's your fault, not mine. Okay, so I think it's fair to say that pretty much everyone in this room has more than one computing device at this point, whether that's a laptop, a desktop, a smartphone, a tablet, a smartwatch, intelligent sneakers, an intelligent bathroom scale, a smart refrigerator. And this makes things way more convenient. Like if you're traveling to give a talk, you can decide, hey, I'm just going to bring my tablet with me, and I'm going to work on that, so it's easy to travel with. But at home, I've got a big, powerful desktop that I can watch movies on a giant screen and have my ID on another window, and etc. So it makes things way more convenient. But that convenience gets turned on its head when we start trying to use strong cryptography, and in particular, end-to-end cryptography. The reason for that is that with end-to-end crypto comes these long-term identity keys. These are just private key files that represent our identity in some way that we need to use in order to interact with any app or application that we want to be ourselves in. So, if you have like email or something, you need your signing key and so on. And so for one thing, we need to be able to access these keys from all of our different devices, which in itself comes up with a problem of, how do we store these securely? How do we transfer them between devices securely? I bet you that people that use secure email, some people have definitely emailed their private key to themselves to transfer it to another device. Think about what you've done. It's your email key. So, of course, we've got this management problem, and we can kind of build software to deal with, making this more convenient and stuff. But then there are other problems, like what happens when one of your devices gets stolen? You've lost access to your key. The attacker can now use it to impersonate you because it represents your identity somehow. They might be able to access your files. And in addition, you have to revoke this key if you've gone and verified manually with people, like, hey, this is really my key, like in person, you've got the right one. You've got to do that all over again with everybody you communicate with. It's a huge pain. And so every new device that we get where we want to use this key from, this problem gets magnified with each one we add. So I'm going to talk about a solution to this problem tonight. It is kind of tough. Facebook very recently released this thing. I think they just call it Secure Chat, which is a very creative name. And for the multi-device problem that I'm describing, they completely punted on it. They decided that you can only use secure chats from a single device at a time. So this is a problem that a lot of people are having trouble with and working on. So let's suppose we've got some key represents our identity somehow. Just for this example, I'm going to say that this is a signature key. So I can create a digital signature so that other people know is authentically signed by me, as long as I have access to this private key. Now I have lots of devices. I want to be able to use it from all of them. What are my options? The naive option is, of course, simply copy it to all of my devices. This has a lot of the issues, like I just mentioned before. A lot of people do it manually, so that has issues by itself with transferring. There's a software product for email called whiteout.io. That does it. That actually does it nicely. It makes you encrypt things with a strong, randomly generated passphrase. You just have to type it in once on each new device you add. But it still, of course, has this problem where if you lose a single one of any of these devices, you have to that's a catastrophic failure. One key is the same as all of them. So if an attacker gets one, they can impersonate you. You have to revoke every single one of the devices. You have to generate a new key. You have to sync it to all of them again. Lots of problems. Another approach, you could generate a unique key for every single one of your devices. Interestingly, this is actually what Apple iMessage does. If any of you use that, it generates a different key for each of your devices. And so the nice thing here is that suppose one of these devices gets stolen, then we still need to revoke a key, but we only need to revoke one. So in this scenario with 4 keys, if the cyan key gets stolen, we have to revoke the cyan key, but we still have these 3 other keys that we can use. Maybe we can do some bootstrapping where we tell people, hey, I lost this key, and I can prove it using these other ones, something like that. But there's still this problem where just by stealing one device, the attacker has a key now that they can use to impersonate you. There's also a privacy problem in this scenario. which is that you're signing messages, outgoing messages, with a different key depending on which device you're on. So if, for example, you have a home desktop and there's a certain key on that device, and so whenever you sign emails and you're at home, somebody might notice, hey, this person's at home right now, she's signing her emails, and it's got this key, and it's from this key. Then one day you send an email instead from your smartphone. You're going to be signing that with your smartphone key instead. And so the person can look at that and say, oh, hey, they must not be at home today. You know, they're out or they're playing hooky, whatever. So there's a privacy problem with this solution as well. Also, if you're working with PGP, like if you're doing email, a lot of people, like I say, do these things manually. They manually copy their keys. They manually generate them. If you're doing this, then this picture right here represents 4 entries for you in the address book of the person you're communicating with, which is also just a huge usability problem, not just for you, but also for all of the people that you're talking to. So those are 2 of the kind of most obvious solutions to it. There's an academic paper associated with this work in which I look at like a lot of different solutions. Some of them are a little bit ridiculous. Some of them are pretty ridiculous. But I'm going to skip ahead to the interesting one and the title of the talk. So with threshold cryptography, we split the key into these things called shares, and we hand 1 share of the key to each device. This slide is a little bit misleading. You're not actually taking a key and chopping it up by bit. Like, for example, if you have a 256-bit key, I'm not saying, here's the first 64 bits for you, here's the next 64 for you. There's some math involved. But I'm told that you guys are drinking 10% beer, so we're not going to do any math in this talk. I think there's a less than sign in here somewhere, I'm sorry. The important thing to know is that if the attacker steals 1 device in this scenario and they get 1 share, that doesn't tell them anything whatsoever about the actual private key itself. The user themselves sets some minimum number of shares that are required to be combined together to get back the key or to do some operation. Suppose that, for example, we have a 256-bit key. The user sets the threshold to 2. It's not the case that the attacker goes from having to do, It's not the case that the attacker goes from 2 to the 256 work down to 2 to the 128 work. It doesn't chop the work up like that or anything. If the attacker compromises less than this threshold number of devices, they don't learn anything whatsoever about the key. So let's suppose that this user in our example wants to create a signature. And let's suppose that their threshold number that they picked, they just pick it based on their number of devices. Let's suppose it's 2. If they want to sign an email in this case, they have to pick any arbitrary subset of 2 devices. Get them together. Getting them together in this case doesn't mean necessarily physically, as long as they're able to interact with each other over the internet, over Bluetooth, whatever, that's good enough. And these devices work together. And in the simple case, what they can do is use this primitive called threshold secret sharing. A lot of people have heard of Shamir secret sharing, for example, which is when you take just a secret and you divide it into shares, and then a subset number of people working together recover that secret. That's secret sharing. And so in this case, we would secret share the private key itself, and then when we want to use it, we just have a few devices work together, we recover it, we use it to do something like create a digital signature, and then hopefully the device using it throws that key out of memory. However, we can actually do one step better than this, because the problem there, of course, is that this key right here is actually sitting in device memory at some point. It might be the case that, maybe there's malware running on one of these devices monitoring memory, and as soon as it spots that key there, it says, hey, I'm going to save a copy of this, send it off, whatever. Could be the case that the FBI is sitting there watching you, waiting for you to send an email, and they run in and they grab your smartphone out of your hand and they drop it in a bucket of liquid nitrogen. This is the stuff academics like to do. People have actually tried this, and you can do it. So we have to worry about attacks like that. The FBI dropping your phone in liquid nitrogen. So we can, like I say, we can go one step further, and we can use a threshold algorithm specifically designed for the thing we want to do. So for example, in this case, we want to create a digital signature, and so we would use a digital signature algorithm. The only difference between this and threshold secret sharing is that the output of the algorithm is not the original private key itself. The output of the algorithm is actually a digital signature. If we're using a threshold decryption algorithm, the output would be the decryption of something decrypted with the private key. If we were using a threshold authentication algorithm, the result would be authenticating with a service, not actually recovering the private key in memory. So, like I say, much better, protects us against dropping your phone in liquid nitrogen, protects against malware running on the device. The catch is that we now need a threshold version of every algorithm that we actually want to get a result from. So for this work, we created this thing I called Shatter. I called it Shatter because it's reminiscent of breaking things into many pieces. I'm very clever. So Shatter is two things. It's both a library and a suite of apps, and I'll talk more about why it's two different things. But the intent of it is to protect these private keys and protect user data by splitting them up against devices, exactly like I said. So the important numbers here, and this is where the less than signs come in, the important numbers here are N, which is the number of devices that you have, and T, which is the threshold number you pick. The user themselves chooses what they want T to be, so they can pick any number, at least 2, because if you pick 1, then you're just doing nothing. And up to N, because you can't have a subset of more than the number of devices that you own. So like I say, the user picks T, and the property that we want is that at least T devices have to work together in order to perform any operation. We want it to be that the act of participating in an operation doesn't result in the private key being placed in memory at any point. And we want it to be the case that if an attacker compromises less than the threshold number of devices, they don't learn anything about the private key. So just to expound on that a little bit, let's suppose in this example that N is once again equal to 4, and T once again we'll say is 2. So suppose that we lose one device, or an attacker steals it, or they compromise it somehow, whatever. If we lose one device, the attacker can't do anything. So in this example, we've got 3 devices left. So as soon as we notice that one device has been compromised, we go take any 2 of our remaining 3 devices, and we revoke that one that got lost. The attacker gains nothing. Suppose the attacker gets control of 2 devices. Well, in that case, yeah, the attacker gets your private key. This is a compromise. They've compromised T of your devices. So they get your private key, but the nice thing here is we still have 2 devices left. So for example, if you're doing threshold encryption, encrypting all your data, then the nice thing here is that you can still use your other 2 devices, your remaining 2, to get your data back. So the attacker gets your stuff, but you at least get a copy of it as well. The really bad problem comes in when you have less than T of your devices. And this is a catastrophic failure akin to losing your one device in the single device scenario, or all of your devices in the multi-device scenario. The nice thing here, of course, is that you can set T to a different number depending on the number of devices you have. So in this scenario where the attacker has compromised at least T devices and we have less than T remaining, we lose our own data as well. There's no way for us to recover from this. So just to formalize the properties that we want to get out of Shatter. We want backwards compatibility. So what I mean by this is that, so Shatter is not a new messaging app, for example. It's not a new instant messenger that you have to convince all of your friends to switch to. The idea is that if, for example, you're all using WhatsApp, which does have end-to-end encryption now, if you and all your friends are already using WhatsApp, you should be able to switch to this Shatter-compatible version of WhatsApp and start using threshold crypto without having all your friends switch to it as well. In fact, ideally, they shouldn't even be able to tell that you're using this thing called Shatter. They shouldn't even know it exists. So we want backwards compatibility with existing software. And the challenge here is frequently that we need to use the cryptographic algorithms that the software is already using, which means that, for example, if an app uses RSA signatures, we need a threshold version of RSA signatures. So that's where the challenge comes in for backwards compatibility. We want device anonymity. So I showed, for example, the case where if you're using two different devices with two different keys, a person can just look at which one you signed with to see which one you were on at the time. We don't want the person to be able to tell that you're communicating with to be able to tell which device you're on at the time. iMessage, like I say, uses that system of a different key per device. And so you can actually tell, if you know how to go in and look at the protocol, which device a person sent an iMessage from. And you can actually get a list of all of the devices they have in total, even if they haven't used one in a very long time. And so Shatter itself does have both of these properties. So I talked about theft resistance, and this is a very wordy slide just to formalize it. The basic idea is that we want to require attackers to steal or compromise at least T of our devices, not just a single one. But I also added a little bit of extra distinction here between weak and strong theft resistance. The key here is, so there's an interesting idea here where if you have a bunch of devices that you have in a group to do threshold crypto with, and you say, hey, could you, and you, please participate with me, and I need at least two of you to agree. In software, the software can automatically say yes. It doesn't necessarily have to ask you, do you say yes or no? So imagine that I set up, as the user, I configured all 4 of my devices to say, whenever you get a request to participate in a threshold operation, just automatically say yes. Don't ask me, don't wait for confirmation, just automatically say yes. In this scenario, with T equals 2, the attacker steals 1 device. They can actually, sign emails, for example. They've got this 1 device, they can send a request to another one, and if it automatically says, yes, I'll participate, they get an email signature back. So we say that something is weakly theft resistant if it only protects you against the scenario when devices don't automatically participate. We say that something is strongly theft resistant if even when devices automatically participate, they still don't get the private key out of it. So this is the difference between that secret sharing version I showed you where the private key shows up in the memory of the device and the threshold signature version where it doesn't ever show up in the memory. So in the case that the attacker steals 1 device, they can use that to generate a whole bunch of signatures. They might get like 1,000 email signatures in the time it takes you to discover that they've stolen your device and that they're using it. But even after generating 1,000 signatures, they don't actually have your private key. So they can't, once you revoke that device, they can't use your key to generate another 1,000 more. So Shatter, our goal is to have both weak and strong theft resistance. A few last properties we want our solution to have. We only want there to be a single public key. We don't want the user's address book to have a bunch of entries for all your devices. We don't want them to be able to inspect the protocol and see all your devices. We don't want them to see more than one public key representing your identity. We don't want there to be any concept of a master device, a device that's more important than all the others. Some of the solutions we looked at had one of your devices act as like a certificate authority where it issues credentials to your other devices. And of course, this means that one of your devices is extremely sensitive to theft as compared to the other ones. And so we don't want anything like that. We want all the devices to be equal in our solution. So Shatter has both of these first two properties. We fall down a little bit on only having one active device. So I need to admit, of course, if you're, for example, sending an email on your phone, ideally you don't want to have it be the case that a bunch of your other devices have to be powered on and connected to the internet. That is an inconvenience, and that's the trade-off that we have using threshold cryptography in the single user scenario. So we do fall down a little bit on that. However, there's kind of a trick you can use to get some of the protections of threshold crypto. So the trick is to use some sort of cloud provider that's always on, always connected, and treat that as if it was one of your devices. And then, of course, set t is equal to 2. So in this example, you've got your phone, and we've got some Amazon cloud service that we've installed Shatter on, and it's acting as if it were a device. And there's another nice little trick that we can do, which is we can tell our phone that the Amazon client is a cloud provider. And so with cloud providers, we say they're not allowed to initiate requests. And so we say to the phone, hey, if you ever get a new request, like a request to sign something from a cloud service, just don't accept it. Don't even ask the user about it. Ignore it. And so if it turns out that Amazon is evil, no comment, then it means that they can't go grab your key share, initiate a request, do something as you. Then, of course, if your one single device gets stolen, what happens to your key? Well, they can probably still log into Amazon and act as you, but one option is to generate another share and just print it off. So you print it off as a piece of paper, you put it in your safe at home, your safe deposit box, you put it wherever you keep your birth certificate. Hopefully that's somewhere secure. And then in the case that you lose your phone, you go find your backup share, you use that to log into Amazon and recover your original key, which will give you, at least give you your data back. So like I said before, Shatter is both a library and a set of applications. The applications are, for one thing, these things we call Shatter clients. Shatter clients are the thing that you use to manage your set of devices, like say, this is my device, this is not, add a new device, revoke a device, etc. At the moment, our software runs on Windows, OS X, Linux, Android, Android Wear. I'm trying to find an undergrad to implement it in iOS for me. So hopefully that will be soon. And the reason we want to support a lot of platforms is so that you can be running Shatter clients on as many devices as possible, so that you can set T and N to be as high as possible. You really want T to be as high as you can conveniently support in your day-to-day life. So, maybe you can't send email on your smart sneakers, but there's no reason that your sneakers can't participate in complex threshold crypto operations. That's a weird sentence. And the other part of Shatter is we created a library so that people who make applications like instant messengers, email clients, data storage apps, whatever, can just drag and drop our library in and say, hey, whenever you want to do some crypto, instead of using the normal crypto library, use Shatter instead. So just to show you a few examples of what it looks like, this is the Shatter client running on Android. The Shatter client, like I say, takes care of enrolling new devices, revoking devices you've lost. Those are threshold operations, by the way. If you lose a device, you need to have T remaining and working together in order to revoke a device. Same thing with enrolling new ones, you just need to have T. Changing the threshold is a threshold operation. So if you have the Shatter client running on the device, it deals with pairing all of your different devices. It deals with receiving requests from other applications on the device to perform threshold operations. And it, it does all the crypto. It communicates with all of your other devices. If it receives a request from another one of your devices, it pops up a notification saying, hey, if you've configured it that way, it'll say, hey, do you want to accept this request or not? Of course, you could just configure it to say yes every time, just a configuration thing. And there's an interesting thing that the screenshot shows and kind of points out, which is that you have an audit log of requests that the device has received previously. And this is especially interesting in the case of auto-accepting devices. So in the example where you have all of your devices auto-accepting and only one of them gets stolen, but your threshold is 2 or more, the attacker can, get a bunch of things signed or decrypt a bunch of things or whatever. They can do a bunch of bad stuff, but they need to communicate with your devices that you still control in order to do that, which means it's guaranteed that you have an auditable log of the things the attacker did while they were in control of your device, which I think is pretty cool. I almost tried to drink water from the microphone. Okay, so some of you might have played with Intel Edisons before. They're a lot of fun. These are Canadian quarters for scale. The Intel Edisons are meant to be Intel Internet of Things platforms. This cord here is just running for power. There's no data going over that. I just didn't have a battery nearby when I took this picture. This is just running as a Shatter client with a pop-up saying, hey, do you want to accept or reject this request that we got? Very easy to do because the Intel Edisons just run a normal Linux distribution. All I did with this one was install Java on it, because that's what Shatter is written in. And then I spent like 20, 30 minutes writing a wrapper in C to make it actually display the output on the screen. It was really simple. So yeah, like I say, it is running wirelessly, just needed power. This is an example of the Android Wear client running on a Moto 360. The Moto 360 is kind of nice because it can connect to Wi-Fi on its own. Most Android Wear watches need to proxy through your smartphone's connection, which does some really interesting things to the threat model, actually. If you think of a watch proxying through a phone and connecting to another one of your Shatter devices, and both your watch and your phone are Shatter devices, are they really a separate party in that case? It's an interesting question. So the Moto 360, by using that as a Shatter client, removes that interesting question, allows us to sidestep it and just connect to other things directly. So the first algorithm that we implemented was DSA and also ECDSA. And this is actually a very new algorithm. It was just published in the last year. I actually sat down and started trying to come up with it myself, and someone beat me to it. And so you might think, so DSA, the digital signature algorithm, why would you choose that over, say, threshold RSA, which has been around since 2000? The reason is for backwards compatibility. We're constrained by the algorithms that are used in the apps that we're trying to augment with threshold crypto. So there's this very popular protocol called off-the-record messaging, which is end-to-end encrypted. And the way it gets its authentication in the protocol is by a single DSA signature at the very beginning of a conversation. And so if we want to take the authentication from that protocol and distribute it with threshold crypto, we need a threshold version of the DSA algorithm. So we implemented this algorithm by Gennaro, and we added it to this app called Chat Secure, which is an OTR client. It was an extremely popular OTR client for Android. They just discontinued it a few weeks ago, unfortunately. But I think they're going to be, there's a group that's going to be forking it and continuing support for it, so it will live on. A much more popular end-to-end protocol is called the Signal protocol. Many of you have probably heard of it. There's this app called Signal, which also does end-to-end crypto. Their protocol is based off OTR, but it changes the handshake with the DSA signature in it, so it no longer uses DSA. It does this thing with, it's called a triple Diffie-Hellman handshake. And it turns out that the triple Diffie-Hellman handshake is actually extremely easy to make a threshold version of. It's so easy that we didn't bother for the paper. It's extremely fast too, but we do have a version of Signal that uses threshold crypto as well. That protocol, incidentally, is what powers the end-to-end crypto in WhatsApp, Facebook Messenger's new thing, Google Allo's new thing that they're coming out with. So all of those new end-to-end encrypted products are using the Signal protocol. And so we do have a threshold version of that ready to go as well. But I'm going to talk about the DSA one for now. So this is what Chat Secure looks like. This is what our modified version of Chat Secure looks like. And it's an incredibly boring screenshot, which is good because the intention is to show that the user experience of these applications is pretty much unchanged. So this is just a chat application, two people talking, me and me. When the person turns on encryption, depending on what they have, how they have Shatter configured, as soon as they hit that start encryption button, Chat Secure will send a message to the Shatter client running on the same device. It'll say, hey, could you please sign this for me with DSA? The Shatter client sends a bunch of notifications to all of the other devices of yours that it can reach. Once T of them participate, either by you getting a notification and saying yes, or by them automatically saying yes if you have it configured that way, as soon as it gets T-1 others, the Shatter client works together. There's a couple of rounds of just math being exchanged. And then the result is a DSA signature, which the Shatter client then just passes back to the Chat Secure application and says, here you go, do whatever you're going to do with a normal DSA signature. So like I say, the most interesting thing about this screenshot is that it's pretty much a completely unchanged user experience. They still have to go and click Start Encryption. If they have all their devices configured to auto-accept, and that many are reachable, then the user experience is completely unchanged, except for a small delay before the lock icons appear, which means that everything is secure and you should trust it. So the next algorithm that we implemented is encryption, specifically threshold pi-a encryption. If there are any cryptographers in the audience, one, I'm sorry. Two, this is kind of a weird choice. Threshold pi-a is a public key encryption system, and it's kind of slow compared to some of the other choices that we could have used. The reason we chose it is because it's a subcomponent of the signature algorithm that we used. So the signature algorithm actually uses threshold pi A encryption. So we already had it implemented. It was ready to go. So I thought, hey, we already have this thing implemented. It's in Shatter. Let's just show the robustness of this library by making it do something else. So that means that Shatter now has support for encrypting and decrypting arbitrary plain text using this algorithm. So we modified a note-taking application. It's called OmniNotes. It's just one of those apps where you can create new notes, write arbitrary text in them, and save them, pull them up later, search them, whatever. And so it's just a way of showing that we can encrypt arbitrary data on your device. You could think of it as files if you wanted. And so because threshold pi A is a public key encryption system, that means that you can encrypt things using the public key, which means that saving notes, like once you've done writing your note and everything and you want to just save it back to the device, that is not a threshold operation. That can just be done instantly. It's opening notes and getting back the plain text of them, decryption, that is a threshold operation. So once again, I have a very boring screenshot. Mostly looks exactly the same as vanilla OmniNotes, with the exception that there's now a lock telling you that it's secure and trustworthy. That's what locks mean. So in this case, so OmniNotes already came with the ability to encrypt notes with a password. We just replaced the call to asking the user to type a password with asking them to do this threshold operation. And so the user experience for encrypted notes goes from having them type in a password to having them either click yes on a couple devices or maybe even just it automatically happens if they have it configured that way. So once again, the user experience is not too significantly changed. I also found while going through the source code for OmniNotes, I hope none of the developers are in the room, but their encryption algorithm was equivalent to plain text. So we also fixed that. So this is based off an academic paper. Academic conferences always want evaluations, so we did it. So we evaluated the two algorithms I talked about on a desktop machine with some specs that are great, some Nexus 5 smartphones, and also the Moto 360 that I showed you a picture of. This evaluation, we set t to be equal to 3, and then we used a bunch of devices with 3 combinations of devices. So we tried it with 3 of our fancy, powerful desktops, 3 phones working together, and also a desktop, a phone, and a smartwatch working together. So these times are in seconds, and they're kind of big. They're kind of large values. 13 seconds to do an operation if you're using a desktop, a phone, and a smartwatch. Only a couple seconds to do decryption, much better. So I want to say a few things about these values. First off, they're usually done for rare operations. So for example, if you're doing secure email, then you only need to do the threshold operation when you send an email to sign it. Gmail actually gives you this ability to artificially delay your email by 30 seconds anyway, in case you regret sending it within a few seconds and you can hit cancel. So they clearly don't think that 30 seconds is too bad for sending an email. For having conversations over instant messenger, I talked about OTR. In both OTR and the signal protocol, the actual threshold operation is only done at the very beginning of a conversation. So when you send that first message, you say, hey, are you around right now? That's when the threshold operation happens. It doesn't happen again for every single message. So overall, these are somewhat rare operations. Also, however, while we were implementing these protocols, we realized that the majority of threshold protocols have these things called zero-knowledge proofs associated with them. Zero-knowledge proofs are a bunch of math that takes a long time, but is required to show that none of the devices participating have been misbehaving. Like, for example, if you're working with DSA and we say, hey, you're not allowed to set E to 0, make sure you don't, and someone does, then the zero-knowledge proofs allow us to find out they did something wrong without actually finding out their secret value, the value of their share. And so they're necessary for the security of the protocol and to detect misbehaving people, but they're not actually necessary for getting the result of the threshold algorithm. So you can actually say, if you're doing a signature, you can run the threshold signature protocol, get back an actual signature to stamp onto a message, and then check the zero-knowledge proofs to see if anyone did anything bad. And so that leads kind of to an interesting implementation decision. So like I said, they're very time-consuming, and they take the vast majority of the time. So this is the column I just showed you. This column shows how long things take just to get a result without checking, without creating or verifying the zero-knowledge proofs. And so you, as the developer who is choosing to add Shatter to your application, you have a decision to make, a security decision, which is to ask yourself, can I get away with deferring the checking of these zero-knowledge proofs? For example, if you're doing email signatures and you say, hey, I'm not going to check the zero-knowledge proofs right away, I'm going to wait. I'm going to take the signature, however, and send the email. Maybe sending the email reveals information to the attacker, that misbehaving person, that could be very bad. So that's probably not a good case of you being able to take advantage of that optimization. But in the case of the OmniNotes application, where all you're doing is getting back a decryption of something, and in fact, you're actually getting a decryption key back, and then it's hybrid encryption, and so you're then also decrypting the file with that. You can actually just check, hey, did this decrypt properly immediately? You don't have to wait to see if anyone's misbehaving. And so in the case of OmniNotes, where you can do very fast decryption, in that case, you can just immediately show the result to the user, get the advantage of this 100 millisecond time delay, and then if it turns out 2-3 seconds later, hey, one of the devices is misbehaving, then you take some sort of action. Whatever that action is a very complicated question in security. Do we just tell the user about it? Do we revoke it ourselves? That's a hard question, but from the user experience perspective, if you're able to defer these proofs, you get a huge benefit out of it from the user perspective. Bandwidth is extremely small. All of the messages range from anywhere from 4 to 16 kilobytes, not very much. In the case of doing signatures with our DSA algorithm, they take 6 times T messages. The way this works is your one requesting device sends a partial computation to all of the other devices. So it sends it out to T-1 devices. It gets back T-1 and a couple of rounds of this. And decryption, it's only one round. You send out a message to everyone else, you get a message back, and that's it. And these messages are all sent in parallel. So if T is set to 2, and then later you set T to 100, the time doesn't go up that much more by setting T to a very large value, because all of this computation is done in parallel with each of the devices. It does go up a little tiny bit, but compared to the communication cost, it's negligible. So I'll conclude there. Like I say, we made this thing called Shatter. Protects users with all of these wonderful, cool protections I talked about. It does it in a fairly seamless way, I like to think. I paid a bit of attention to usability while working on it, as you saw. We already have algorithms available for doing DSA signatures, ECDSA signatures, public key encryption, and not mentioned on the slides, but also for the Signal protocol. We have Shatter-aware versions of these 2 apps, Chat Secure and OmniNotes, and Signal. And it's free and open source, because all of the work that I do as an academic is free and open source. You can get the source code, play with it. Thank you.
Okay. So could you talk a little bit about key generation and distribution? Like, do you need to generate the whole key first and then distribute parts of it, or is the generation actually distributed? And also, what happens when you buy another device and you go from n to n+1?
Good question. So key generation in the initial step, you can, in fact, just have one device generate a key normally, split it up into shares if there's an algorithm for it, and then hand out a share to each device and delete them from memory. And in fact, that is what we're doing in Shatter, but only because I'm a lazy grad student. There are, in fact, threshold key generation algorithms that you can use where you get all of the devices, you need all n devices working together at the time to generate shares of a key where that original key was never actually in memory on any one of the devices, and none of them can learn it without doing the threshold operation. So those algorithms exist, and we certainly could use them. And because initial pairing and enrollment and revocation are rare events, it doesn't even matter if they're kind of poor performance. Like, even if it takes minutes, that's probably fine. So those exist, and we could certainly be using them, and we'll get around to adding them at some point. For enrollment of a new device, actually, let's do revocation first. So suppose you lose a device. So again, if you lose a device, you could just take T devices and recover the original key in memory, split it up again as if you're doing a completely new initialization, and hand out shares to the people that are to your devices that are remaining. And that's also, again, what we do in Shatter at the moment. There are, again, algorithms called threshold key resharing algorithms. Those are a little bit trickier, however. The initial key generation is kind of easy. If you're doing Shamir secret sharing, there's a very well-known redistribution algorithm for having everybody generate a new share minus one person. To my knowledge, nobody has figured that out for DSA yet, because like I say, the algorithm is only a year old, and it has to be figured out all over again, basically, for each new algorithm. And then revocation is the same thing. Does that answer your question?
So I had a question about, whoa, jeez. There we go. So I had a question about active and passive adversaries. So in the case of if you are a global adversary and you can see the plain text communications between devices as they perform operations, does the adversary learn anything in that case? Or in the case of, let's say, an active adversary where I have compromised the device and now I'm actively participating in these operations but providing, let's say, like malicious or incorrect responses to those operations, does the adversary learn anything in either of those cases?
So first I can short circuit your question. There is no plain text communication between the devices. When we pair them initially, we have them share a key for each other, and then they actually do end-to-end encryption with with each other whenever they communicate like that. And so you shouldn't actually be able to intercept the plain text communications. If you could, though, that would be the same as, so you've got T devices, but you're only communicating with T minus one of them. So there's the initiating device and then communication to the other ones. And so an eavesdropping adversary, even if they could see plain text, would only see T minus one communications, which is the same thing as the central device sees. And so maybe they could, in some algorithms, they could construct the thing that you're trying to construct, like just a single signature. I would have to sit down and look at it to figure it out. But most of the time, they just shouldn't be able to. And they certainly can't get the actual private key itself. There's one more part to your question.
Active adversaries who who would respond to operations with either incorrect or possibly malicious answers.
So that's what the zero-knowledge proofs I mentioned are for. As long as you know all of the possible bad things that a malicious participant can do, then you run, as long as you can enumerate them, you can also include a zero-knowledge proof to say, did you do this or not? Prove to me that you didn't actually do it. And that's what those zero-knowledge proofs are. There's some algorithms where we think they're not even necessary whatsoever. However, the actual protocols have security proofs, and they turned out to be necessary for creating the security proof. Whether or not they're actually necessary or not, it's something I argue with one of my committee members about, like, at least once a week.
Gotcha. All right, thank you.
Yeah. I think you're supposed to throw it. Yay.
Hi. Sort of, I guess, to go off that with the a sort of like if the traffic between devices is being captured, if one of the devices is compromised but it's not acting in bad faith but simply says like I would like to start a communication, does that mean that you would have, like if I have 4 devices and you're on device 1, 2, 3, and 4 will send their components. I have device 1, and so the part 1 of the key, do I have the full key, or is there still kind of more work to do? And that may be incomprehensible, I'm sorry.
So if you've compromised one device and you do one of these operations, even if you and it works and you get a result, like say you say to everyone, hey, please help me sign this message.
Right.
Then yes, please help me sign this message. And they participate, you get out a signature of the message. But you shouldn't get out anything else. You should be able to sign thousands, tens of thousands of messages and never learn the private key.
Got it.
I think at some point you hit a certain number where actually it becomes easier, but it's like millions or billions or something.
So I could sign something, I could sign something going forward, but I have no access to anything previously signed, per se.
Yeah, everything should be tossed out of memory too from the past. One thing that you could potentially do is initiate, say, a new enrollment or a revocation, which, like I said, those algorithms are a bit complicated, and so at the moment what we're doing is recovering the actual original private key. And so the way we've dealt with that for now is that you cannot make a device, you can't configure a device to automatically accept enrollment or revocation requests. We require the user to manually go click the yes button on those.
Got it. Thank you very much.
Cheers.
Okay, it looks like we have a question from one of the YouTube viewers.
Cool.
If one already has a PGP, public key, can that be used with Shatter?
The software doesn't support it, but I think yes. What are PGP? PGP signatures you can make an RSA or a DSA public key. RSA is easy, so yeah, we could totally add PGP support to it. We haven't yet, but we could use this algorithm even to do it. It would mean diving into the PGP key format, which is awful, but yeah, we could do it.
So this might be a silly or unanswerable question, but especially given that like the DSA algorithm is only a year old, how confident can we be that they will actually sort of long-term live up to the kind of theft resistance properties that you enumerated?
Good question. Good thing to think about. So the paper itself is written by, the Gennaro in the Gennaro et al. Is Rosario Gennaro, who's a very well-known and well-established cryptographer, has a great reputation. I trust them to come up with good protocols. It also is a very long paper and does include a security proof of that protocol as well. So as long as they didn't make any mistakes, which, it's a peer-reviewed paper, so nobody's spotted one yet, the protocol itself should be good. Our implementation, of course, is another matter. Maybe I made some mistakes when I implemented it. With all strong security software, you should, at the very least, look for an audit of the source code. There hasn't been one of Shatter. There probably won't be one anytime soon. Not even that many people have looked that closely at my source code, looking for security bugs. So don't go download Shatter off the website and start using it to protect like your company secrets. It is, I'm a grad student. We like to call our software gradware. I should change the URL even to gradware. Maybe I'll make it an alias. But yeah, this is very much meant to be like a research prototype. Don't actually depend on it. But by all means, help, I guess.
First off, thank you so much for your time and sharing. And I guess my question kind of goes a little bit with what he shared, like if I send a request and all these devices respond, I think that will be only in the case of the auto-respond devices. If my understanding is correct, I send a request, but I as a user need to initiate that response on another device. So what would be a use case for the auto-response that you mentioned? And can you have both auto-respond and manual respond depending on what application I'm using?
Yeah, good question too. These are all really good questions. So the way I personally envision it, I think having a mix of some devices automatically accepting and some not automatically accepting, some requiring a manual intervention, is a very good idea. So for example, I have a desktop, a big powerful desktop at home that's always online and always connected. And I think that would be a very good candidate for a device that automatically accepts. Because it's at my house, it's behind a locked door. I treat my belongings very, I treasure them. I do things to make sure they don't get stolen. I lock my door. I have like a security guard in my building. And so I think that's a good device to automatically say, yes, sure, participate, however you want. However, something like my phone, which I'm always setting down, never quite sure where it is. Maybe not such a good candidate for automatically accepting requests. Yeah. Thank you for your question.
So wouldn't the concern for an auto-accepting device not be that it can be gotten to, but that another device that can be gotten to will request it to participate? So your computer at home might be locked up, but if your phone gets broken into, then your computer at home is going to participate in that algorithm.
That's a very good point. Yes, and in fact, maybe I guess the way I should have phrased it even would be you want to, I'm just thinking of this off the top of my head, invert that relationship. Where you say if you've got a device that, because like I said, when you initially set up the devices, you set up identity keys for the devices themselves as well, so they can both communicate securely and also authenticate who the other devices are. So like in the case where I talked about a cloud provider, I said you don't want to accept requests that are initiated by that. Maybe you want to do a similar thing with your devices. But then you have to wonder, that's a good point.
Anybody else? All right.
Not that this is ready for mainstream use, but if it were to be ready, what use cases do you expect the general public to use? Like 2 devices being T or 3 or?
So, I mean, for me personally, 2 is probably the best number that I could support. I don't wear a watch at all. My tablet is bricked right now. yeah, so I basically have 3 devices. I definitely don't have my laptop on all the time, so T is a good number for me. There's some really interesting work by a professor named Frank Stejano at the University of Cambridge. And he's doing something kind of similar, but not with powerful devices like I use. His idea is that you build wireless chips into like earrings and shoelaces and your belt buckle and all of these things, and you have them on you all the time, so you can set it to a much higher number. So as long as you're wearing at least 5 accessories that day, then you can do a threshold operation. So yeah, if things like, smart Internet of everything you're wearing becomes very prevalent, we can certainly up T to more. But I think, well, for one, making it user configurable is very important. And I also think, at least personally, T equals 2 is, for me, a good number. I've never lost more than 1 device at a time. Like, I've lost a phone before. I had a laptop stolen from a dorm room one time. But I've never actually lost 2 devices at once. And so, yeah, for me, it would be a good number. For you, it's your threat model, so who knows? Thanks.
Is this, let me see. So this is going to be really silly. You know the Pokemon Go bracelet thing? Where they like hit the button and it catches the Pokemon?
What?
Yeah, okay, that will be silly. Let's say we had an Internet of Things device, has wireless communication, an active trigger. Could you have a couple, you say like a belt buckle, earring, or whatnot, and you have something you can say, all right, trigger communication, triggered on my wristband, belt buckle, grab my earlobe, everything comes together, forms Voltron, everything's fine. Does this, I guess, how many places can this go? I guess, this is going completely off the rails. How small of a device, how much memory, how small can we get with it in terms of a device that can participate in the sharing safely and be part of your, the share, I guess?
So, like I say, my work is mostly concerned with very powerful devices. Like, smartphones are better than the computer I had when I was 12 now. So, they're ridiculously powerful by all relative standards. But the work I talked about before, Frank Stejano making earrings and belt buckles, his work is obviously very interested in making low power, high battery life devices. And in fact, one of the people on my committee at Waterloo, Ian Goldberg, worked with him on a project recently where they tried to see how they could stretch this out. The devices they made were I think this big-ish, which is, a prototype, obviously. They had something like 2 kilobytes of RAM, or maybe that was storage, 2 kilobytes-ish anyway of stuff, and the battery life lasted 3 months on them with these little watch cells. And, that's obviously, university prototype, a company with access to a chip fab could push that quite a bit further, so, yeah.
Well, anyone else want anything? I could follow.
So maybe this question will help. When you were talking about incorporating Amazon as a device, we're talking about AWS, like an EC2 instance? Because it almost sounded like you were implying that you could use S3 for this. Is that not right?
Sorry, what's the difference?
S3 is the storage?
Oh, no, it definitely has to have computational ability. That's
Gotcha.
for sure, yeah.
Okay.
Maybe Lambda. I'm sorry, what? Maybe AWS Lambda might be a good candidate for that.
All right, I think we probably have time for one more question. All right.
Also, during the Amazon slide, I think you showed an offline key fragment. Is that again, this not being ready for production, but is that like a recommended practice that you anticipate that people should have offline key fragment backups or that sort of thing, or at least to prevent trust being too much into an external authority?
Yeah, so once again, this, as with all of your questions, this comes down to what your personal threat model is. Like, you know, if you, for example, like if you're a student and you spend a lot of time, like if you spend every summer at home with your parents and you have like a computer there and also a computer in your dorm room, plus like your cell phone, I guess, you know, then having a backup share on a printed piece of paper stored at your parents' house, for example, is not really that much better than you know, having a computer with the share stored digitally on it. Maybe there's not much of a difference there. And so, like I said, if I had computers everywhere and I wasn't worried about an adversary compromising all of these locations, these physical locations at once, I would probably be fine with just digital shares, no backups anywhere. If I don't have something like that, like if I just have my home and a work computer I can't install software on, then I probably would want backup shares put in like my safe or a safe deposit box or something printed off. And also if you're worried about, you know, if your threat model is the FBI vanning you, then they're going to go to your parents' house and they're going to take your computers from there as well. And so if that's your threat model, then again, print them on paper and hide them in a geocache or, I don't know, in a tree root somewhere. What's a good hiding spot? Stuck under a table at Starbucks. No.
All right, everybody. Well, let's thank our speaker. Thank you so much, Erinn.
Thank you.
All right, so next time, don't miss Duotech Talks on November 11th, when we'll have Kelly Shortridge talking about how to become an InfoSec autodidact. Although if you're here, I guess you might already be. But if you're interested in learning more about security, come to our next meetup on November 11th, and stick around, eat our food, drink our beer, and get home safely. Thank you, guys.